Now let's look at a compound with two chiral centers. So our goal is to finish naming this molecule. So if I number my carbons, this would be carbon 1, 2, 3, 4, 5. You can see there's an OH at carbon 2, and there are 5 carbons, so that's where we get the 2-pentanol. And then there's a methyl group at carbon 3, so that's 3-methyl-2-pentanol. But we need to put in stereochemistry, because we know from an earlier video that carbon 2 is a chiral center, and carbon 3 is a chiral center. So we need to use the RS system to finish our name. So let's focus in at carbon 2, and on this drawing on the right will determine the configuration at this chiral center. So here's our carbon, and if there's an OH coming out at us in space, we know there's a hydrogen going away from us in space. And our chiral center is directly connected to a carbon on the left, and this carbon is bonded to 3 hydrogens, so I'll draw those in there. And our chiral center is directly bonded to a carbon on the right, and this carbon on the right is directly bonded to another carbon, and there must be a hydrogen coming out at us in space here. So let's assign priority to our 4 groups. Remember, that was our first step when we're trying to determine the configuration of a chirality center. So here's our chiral center. We look at the atoms directly bonded to that carbon. There's an oxygen directly bonded to that carbon. There's a hydrogen directly bonded to it. There's a carbon on the left, and there's a carbon on the right. So we assign priority based on atomic number. Out of those atoms, oxygen has the highest atomic number, so oxygen gets highest priority. So we call that group a number 1. So the OH group gets a number 1. Hydrogen has the lowest atomic number, so hydrogen gets lowest priority, and we call that group 4 here. So hydrogen is a 4. So now we have a tie. We have these 2 carbons. Let me go ahead and circle them. So carbon obviously has the same atomic number. So to break this tie, we look at the atoms directly bonded to these carbons. The carbon on the left is directly bonded to 3 hydrogens. So we write down here 3 hydrogens. And the carbon on the right is directly bonded to 2 carbons and 1 hydrogen. So we write carbon, carbon, hydrogen. Next, we look for the first point of difference, and that's the first atom here. So carbon versus hydrogen, carbon has the higher atomic number, so this group wins. So this group on the right is higher priority, which means this must be number 2 for our groups, and the methyl group gets a number 3. Now that we've assigned priority to our 4 groups, the next step was to orient the molecule so that the lowest priority group is projecting away from us. And that's what we have here, because the hydrogen is the lowest priority group. So we can ignore this, and we can focus in on 1, 2, and 3. So let me label this on the right. The OH was the highest priority, and this group to the right was the second highest priority, and the methyl group was the third highest priority. Next, we draw a circle and determine whether we're going around clockwise or counterclockwise. So we draw a circle from 1 to 2 to 3. And obviously we're going around in a clockwise direction. And clockwise is R. So we are R at carbon 2. So I write here 2R. Now let's focus on carbon 3. So we know that carbon 3 is a chiral center. So what is directly bonded to this carbon? Well, there's a carbon attached to 3 hydrogens. So there's a methyl group. There's a hydrogen that must be coming out at us in space. On the right, there's a carbon bonded to 2 hydrogens and directly bonded to another carbon. On the left, there's a carbon directly bonded to an oxygen. There must be a hydrogen going away from us, and this carbon is directly bonded to another carbon. So let's assign priority to our 4 groups. So here is our chiral center. We look at the atoms directly bonded to that carbon. There are 3 carbons, 1, 2, 3, and a hydrogen. We know that hydrogen has the lowest atomic number, so hydrogen is the lowest priority, and we call that group 4. Now we have 3 carbons. We have a tie, because carbon, of course, has the same atomic number. To break a tie, we look at the atoms that are bonded to those carbons. So let's start with the carbon on the right here. So the carbon on the right is directly bonded to 1 carbon and then 2 hydrogens. So we write carbon, hydrogen, hydrogen. So in decreasing atomic number, in order of decreasing atomic number. This carbon down here is directly bonded to 3 hydrogens. So 1, 2, and 3. The carbon on the left is directly bonded to an oxygen, a carbon, and a hydrogen. So we put these in order of decreasing atomic number. So we put oxygen first, then carbon, then hydrogen. Let's look at the first point of difference here. So the first atom, we're comparing a carbon to a hydrogen to an oxygen. Out of those atoms, oxygen has the highest atomic number, which means that this group gets highest priority. So the group with the OH has the highest priority. This gets a number 1. Next is carbon, because carbon has a higher atomic number than hydrogen, so that wins it for this group. So this group on the right, this ethyl group, gets second highest priority. And finally, the methyl group would get third highest priority. So now that we've assigned priority, step 2 is to orient the molecule so that the lowest priority group is pointing away from you in space. And here, our hydrogen is coming out at us in space, so that's not what we want. We want the hydrogen to point away from us in space. So one thing we could do is to think about an axis through our chiral center, and we could rotate the molecule about that axis, and that would put the hydrogen going away from us in space. So let's go to the video so we can visualize what happens. So here's our compound. You can see at carbon 2 there's an OH coming out at us in space, and at carbon 3 there's a methyl group going away from us in space. If we rotate about an axis through this carbon, let's go ahead and do that, we can see what happens to those two groups. Now at carbon 2 the OH is going away from us in space, and at carbon 3 the methyl group is coming out at us in space. Let's draw our compound with the hydrogen going away from us. So first we put in our carbon chain, and we know at carbon 2 our OH is going away from us, so here is our OH. And then at carbon 3 our methyl group is coming out at us, so let me go ahead and put that in. So there's a CH3 coming out, and there's a hydrogen going away from us in space. We can't really see it very well in the picture, but we know it's there. So we know that the group with the OH had the highest priority, so this was number 1. We know the ethyl group had the second highest priority, so we say that's a number 2. The methyl group was a number 3, and the hydrogen was a number 4. So with our lowest priority group going away from us, we can now ignore it and see that we're going around in this direction. So we're going around counterclockwise, and that would be S. So we are S at carbon 3. So I could finish off the name by writing in here 3S. So it's 2R, 3S, 3-methyl, 2-pentanol. Now you didn't have to do this whole trick with rotating about an axis. I showed you another way to do it in an earlier video. So let's go back to our original drawing over here on the left. Let me use dark blue. There is a trick that you can use. So if your hydrogen's coming out at you in space, you can just ignore it for the time being and look at 1, 2, and 3. And 1, 2, and 3 are going around this way. They're going around clockwise. So it looks R. It looks like it's R, but since the hydrogen is coming out at you in space, you can just reverse it. You can take the opposite. If it looks R with the hydrogen coming out at you, it must be S. So that's a nice trick, and it means you don't have to rotate the molecule in your head.